You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. In cloud environments, storage is not a one-size-fits-all service. Different applications, workloads, and regulatory contexts demand specialized approaches to how data is stored, accessed, and protected. Choosing the right storage model is therefore about more than just capacity. It is about aligning technology with durability, performance, and security requirements. The three foundational models, object, block, and file, offer distinct trade-offs in structure and semantics. Each was developed to solve different data problems, from storing billions of unstructured media files, to powering databases with low latency, to enabling collaborative file sharing across teams. By understanding these models, learners can make informed decisions about which approach best serves their workload. A poor choice may lead to inefficiency, rising costs, or even compliance risks, while the right match can provide a stable backbone for reliable and secure cloud operations. Storage models can be broadly defined as the way data services categorize and present information for use. At their core, the three models differ in how they expose data to applications. Object storage views each item as a discrete unit with metadata, accessed through APIs rather than file paths. Block storage treats storage as raw volumes divided into fixed-size blocks, directly attachable to an operating system. File storage, by contrast, organizes data into familiar hierarchical directories that allow multiple users to navigate and share files simultaneously. This classification into object, block, and file is not arbitrary. It reflects decades of technological evolution. Each approach optimizes for a certain balance of accessibility, performance, and scale. Appreciating these distinctions helps learners avoid treating storage as a simple commodity and instead recognize it as a design choice with serious operational implications. Object storage has become the workhorse of modern cloud services. In this model, data is treated as an object, which is essentially the file itself bundled together with metadata and a unique identifier. Unlike traditional file systems, object storage operates within a flat namespace, meaning there are no nested folders. This flat design makes it possible to scale to billions or even trillions of objects without hitting directory limits. Metadata is key here. It allows developers to tag objects with attributes such as creation date, owner, or sensitivity level, and then use policies to automate how those objects are managed. For example, a photo-sharing service can use object storage to keep millions of images tagged with user IDs and timestamps, while lifecycle rules automatically archive older ones. The trade-off is performance. Object storage is not designed for millisecond-level latency, but rather for durability and near-infinite scalability. Block storage operates on a very different principle. Instead of treating data as objects with metadata, block storage presents raw volumes divided into uniform blocks of data. Operating systems mount these volumes and treat them like physical hard drives, making them suitable for databases, virtual machines, and other applications that require extremely low latency. The analogy is a blank notebook. Each block is like a page, and the operating system determines how to write and retrieve information across those pages. The lack of metadata means block storage is less flexible for automated policy management, but it offers predictable performance. This makes it ideal for transactional systems where speed and structure matter most. However, because block storage volumes are tied to specific servers or virtual machines, scaling across large distributed systems is less natural compared to object storage. Thus, block storage excels in targeted performance-critical roles rather than in vast repositories. File storage provides a middle ground, focusing on human usability and collaborative workflows. It organizes data into hierarchical directories and allows access through familiar protocols such as Network File System (NFS) or Server Message Block (SMB). This makes it intuitive for users accustomed to shared drives in corporate environments. For example, engineering teams working on design files may need shared access to the same set of documents, with permissions managed at the folder or file level. File storage supports this seamlessly, while still being scalable in cloud environments to some extent. However, as the number of files and concurrent users grows, performance can degrade, and costs may rise compared to other models. Thus, file storage is best suited for scenarios where human access patterns, rather than machine-driven scalability or microsecond latency, drive the requirements. Consistency is another dimension to consider when choosing a storage model. In distributed systems, consistency determines when updates become visible to readers. Strong consistency guarantees that once a write is confirmed, all subsequent reads reflect the update immediately. Eventual consistency, by contrast, allows temporary discrepancies while updates propagate across replicas. Object storage services often default to eventual consistency to maximize scalability, while block storage systems lean towards strong consistency for database integrity. File systems can vary, offering strong consistency within a single share but weaker guarantees across regions. The trade-off mirrors everyday life, choosing between instant synchronization at a higher cost versus tolerating slight delays for efficiency. Applications that require accuracy at all times, like financial systems, demand strong consistency, whereas media archives may tolerate eventual consistency if it improves scalability and availability. Durability is another pillar of storage design. Durability measures how likely data is to survive over time, often expressed in terms of nines. For example, 11 nines of durability translates to a 0.000000001% chance of losing an object in a given year. This is achieved through replication, erasure coding, or other redundancy mechanisms across disks, servers, and regions. Object storage excels here, often offering industry-leading durability guarantees. Block and file storage also provide durability, but their implementations may rely more heavily on snapshots, replication, or backups. The point for learners is that durability is not the same as availability. Data can be durable, safely stored in multiple locations, yet still unavailable due to network failures or outages. Distinguishing between the two helps organizations set realistic expectations and design complementary strategies for resilience. Availability, by contrast, refers to how often a storage service is accessible and functioning. This is typically framed in service-level agreements, such as 4 nines availability, meaning 99.99% uptime in a year. Availability is shaped by system design, redundancy, and failover mechanisms. Object storage often emphasizes durability over raw availability, while block storage tied to compute instances must maintain high uptime to support applications like databases. File storage availability depends on both the service and the client environment, since shared protocols must remain reliable under concurrent access. It is essential for organizations to map these commitments to their business requirements. A service may promise near-perfect durability but still have downtime windows that make it unsuitable for critical, always-on applications. Recognizing this distinction ensures that workloads land on the right storage option for their resilience needs. Latency profiles are also important when weighing storage choices. Latency refers to how quickly the system can retrieve or store data. Block storage typically offers the lowest latency, since applications can access data at the level of individual blocks, which is vital for performance-sensitive systems like transactional databases. File storage sits in the middle, offering relatively low latency but sometimes affected by network congestion or concurrent use. Object storage generally has the highest latency, especially for small objects, as it requires API calls and back-end lookups. These latency differences directly influence workload suitability. For example, video streaming platforms can tolerate slightly higher latency when pulling large media files from object storage, but a payment processing system cannot. Caching strategies can help mitigate latency, but they add complexity, underscoring the need to understand each model's inherent characteristics before committing. One of object storage's greatest strengths is its rich metadata. Unlike block or file storage, where metadata is often minimal or implicit, object storage allows extensive tagging and policy attachment. This enables lifecycle management features where data can automatically transition from hot storage to archival classes or be deleted after a set period. It also supports discovery by allowing users to query objects by attributes rather than by file path alone. For example, a media company can tag video files with attributes like resolution, language, and license expiration, and then use queries to manage distribution. This metadata-driven approach turns storage into more than just a passive repository. It becomes an active platform for governance, automation, and cost optimization. By contrast, block storage's lack of metadata limits its automation potential, while file storage offers only modest metadata tied to file systems. Snapshots are another important mechanism across storage models. A snapshot is essentially a point-in-time image of data, allowing quick rollback in the event of corruption, accidental deletion, or application failure. In block storage, snapshots preserve the state of a volume and can be restored rapidly to support databases or virtual machines. File storage systems use snapshots to capture directory states, enabling recovery of lost or modified files without resorting to backups. Object storage handles snapshots differently, often by versioning objects so that older copies are preserved alongside newer ones. These mechanisms are not replacements for backups, but they provide fast and convenient ways to restore systems to recent states. For administrators, snapshots are like safety nets, not substitutes for parachutes, but invaluable for catching short-term falls. They improve operational resilience when combined with broader backup and replication strategies. Replication plays a critical role in resilience but comes in different forms. Synchronous replication ensures data is written to multiple locations before acknowledging completion, guaranteeing consistency, but at the cost of higher latency. Asynchronous replication, by contrast, writes locally first and then pushes updates to other sites, improving performance but risking temporary divergence. Cross-region replication extends this concept, allowing data to be mirrored across geographic boundaries for disaster recovery and compliance. Each option carries trade-offs. Synchronous replication offers stronger guarantees but can slow down applications, while asynchronous replication improves speed but risks data loss in extreme scenarios. Cloud providers often let customers choose among these models, making it important to align the replication strategy with workload criticality. For example, an airline booking system may require synchronous replication, while a video archive can tolerate asynchronous replication with occasional lag. Tiering policies bring economics into focus by automatically moving data among classes based on usage. In cloud storage, data can be stored in hot tiers for frequent access, warm tiers for less frequent access, and cold tiers for archival. Object storage is particularly well suited for this, as its metadata and lifecycle policies make tiering straightforward. For instance, customer invoices might remain in hot storage for 3 months, then automatically transition to cold storage after a year. The benefit is cost optimization. Organizations avoid paying premium rates for data that is rarely accessed. However, retrieval from colder tiers may involve higher latency or additional fees, so planning is essential. Block and file storage offer more limited tiering, though snapshots and archival solutions can simulate some of the benefits. Tiering underscores how storage decisions are not just technical but financial, impacting long-term budgets and efficiency. Lifecycle rules extend tiering by automating not only transitions but also expiration and archival. These rules are driven by policies that act on metadata or age. For example, a lifecycle rule could state that log files older than 90 days should be deleted, while images tagged as archival are moved to deep cold storage after 1 year. The benefit is reduced manual intervention, minimizing human error and ensuring consistent enforcement of retention policies. In regulated industries, lifecycle rules also support compliance by proving that data is deleted or archived in accordance with policy. The key is that lifecycle management turns storage from a passive utility into an intelligent system that actively governs data over time. Without it, organizations risk accumulating massive volumes of unused or sensitive data, driving up costs and increasing exposure to breaches. Encryption is the final line of defense, protecting data at rest and in transit. Whether the storage model is object, block, or file, encryption ensures that even if an attacker gains access to the raw storage media, the data remains unintelligible without the proper keys. Cloud providers often offer managed key services that automate this process, but organizations may also opt for customer-controlled keys to retain sovereignty. The choice depends on trust, compliance, and operational maturity. For instance, a healthcare provider may require direct control over keys to meet HIPAA obligations, while a startup may prefer managed keys for simplicity. Encryption strategies should also extend to data in transit, ensuring that data moving between clients and storage endpoints is protected. By weaving encryption into every model, organizations add a crucial layer of security that safeguards data integrity and confidentiality. Access control models bind storage decisions to human and system behavior. Identity and access management frameworks allow administrators to define which users, applications, or roles can interact with storage resources. Object storage often uses resource-based policies to control access at the bucket or object level. Block storage relies on operating system permissions once volumes are mounted, while file storage integrates with directory services to manage user rights across shared folders. The principle of least privilege should guide all these controls, ensuring that only necessary permissions are granted. Mismanaged access is one of the most common causes of breaches, such as leaving a storage bucket publicly accessible. By embedding strong identity and role-based access models, organizations not only protect sensitive data but also demonstrate compliance with regulatory standards. Ultimately, access control is the practical mechanism through which technical storage decisions intersect with human accountability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Write once, read many, or WARM. Storage and immutability controls are powerful tools for ensuring that data cannot be altered once written. These features are especially critical in industries like finance, healthcare, or government, where records must remain untampered for compliance and legal reasons. BOERM storage enforces retention by preventing edits or deletions during a specified time frame, making it impossible to quietly modify logs or sensitive records after the fact. Immutability offers similar guarantees but with more flexibility, often allowing administrators to set retention rules and expiration dates. Think of it as sealing a document in a tamper-proof envelope for a set period. Such protections reduce insider threats and accidental deletions while meeting regulatory obligations like SEC Rule 17a-4. By locking down critical data, organizations create an auditable trail that strengthens both operational integrity and external trust in their systems. Integrity verification adds another layer of assurance by confirming that data has not been corrupted during storage or transfer. Checksums and cryptographic hashes generate unique fingerprints for files, allowing systems to detect any alteration, whether accidental or malicious. For example, when data is uploaded to object storage, the platform can calculate a checksum and compare it against one supplied by the client. If the values match, the upload is validated; if not, it is rejected. Over time, integrity checks can also catch disk bit rot, silent corruption, or transmission errors. This process is akin to sealing a package with a unique code and checking that code upon arrival. Without integrity verification, organizations risk relying on data that may have been altered in subtle but damaging ways, undermining analytics, decision-making, or compliance evidence. It is a quiet but vital safeguard across all storage models. Backup strategies remain foundational even in an age of replication and snapshots. Replication ensures copies exist across systems, but it does not protect against deliberate deletion, malware, or systemic failures that propagate errors. Backups are independent artifacts, often stored in separate accounts, regions, or even offline media. A sound strategy, defines what data to back up, how often to capture it, and how long to retain it. For instance, daily incremental backups and weekly full backups might support a database system, while monthly archives preserve historical records. This independence makes backups essential for ransomware recovery, as attackers often target primary and replicated data first. Backup strategies should not be confused with durability guarantees. They serve different purposes. Replication preserves availability, while backups preserve history and resilience against malicious or accidental overwrites. Together, they form a multi-layered approach to protecting organizational data assets. Restoring data from backups is just as important as creating them, and validation testing ensures that the process works in practice. Too often, organizations discover during a crisis that their backups are incomplete, corrupted, or outdated. Validation tests involve periodically restoring backup artifacts to verify they are readable, complete, and meet recovery time objectives. This is similar to practicing fire drills. The existence of an emergency exit plan is useless if nobody knows whether the door's open. In the same way, untested backups offer a false sense of security. Effective restore validation not only confirms technical readiness, but also trains staff in the procedures required under stress. For mission-critical systems, regular drills can mean the difference between a quick recovery and prolonged downtime. It reinforces the principle that resilience is not passive, it is practiced and proven in advance. Namespace design provides order and governance across large storage environments. Namespaces define how buckets in object storage, shares in file systems, or volumes in block storage are organized. Good namespace design establishes consistent conventions, such as naming schemes that reflect business units, data sensitivity, or geographic location. This consistency makes it easier to enforce policies, monitor usage, and scale effectively. Without it, storage environments devolve into chaos, with ad hoc naming leading to lost data, misapplied permissions, or wasted resources. Imagine a city with streets named at random versus one with a clear grid. The difference in navigation and governance is dramatic. Namespace design may seem like a small administrative detail, but it underpins long-term scalability and security. It allows organizations to grow their data environments while retaining visibility and control, preventing the sprawl that often undermines large-scale cloud deployments. Understanding access patterns is critical for optimizing storage performance and cost. Sequential access involves reading or writing large blocks of data in order, which benefits from block storage with high throughput. Random access involves scattered, small reads and writes, such as in databases, and also favors low-latency block storage. Object storage handles large object workloads well, such as video files or backups, but struggles with small object workloads due to metadata overhead. File storage strikes a balance, supporting mixed access patterns common in collaborative environments. Analyzing these patterns helps ensure workloads are matched with the right storage model. For example, analytics pipelines ingesting terabytes of logs may thrive in object storage, while online transaction systems demand block storage. By understanding whether data arrives in a steady stream, unpredictable bursts, or mixed flows, organizations can align workloads with the model that best delivers both performance and cost efficiency. Protocol selection brings further nuance, as it determines how applications connect to storage. Object storage relies on RESTful APIs, such as Amazon S3, which are highly scalable but less suited for low-latency transactions. File storage leverages protocols like NFS or SMB, enabling shared access across multiple systems in a way that feels familiar to users. Block storage uses protocols like ISCSI, presenting raw volumes to operating systems as if they were local disks. Each protocol has strengths and weaknesses. For example, object APIs are excellent for internet-scale applications, but require applications to be written with them in mind. NFS and SMB provide convenience, but may struggle at very high scales or with geographically distributed teams. ISCSI offers performance, but requires careful management of volumes and connectivity. Matching protocol to workload ensures that both application and storage speak the same language, minimizing friction. Performance tuning is often the hidden art of making storage systems truly effective. Queue depths, striping, caching, and concurrency controls allow administrators to squeeze more throughput or lower latency from existing infrastructure. For example, increasing queue depth allows more operations to be handled in parallel, boosting performance for workloads like databases. Striping distributes data across multiple disks or nodes, improving speed for sequential access. Caching layers can reduce latency for frequently accessed data, while concurrency settings optimize how many simultaneous requests can be processed. These techniques require careful balancing. Aggressive tuning may improve speed, but at the cost of stability or fairness among workloads. The analogy is tuning an orchestra. Small adjustments in one section can dramatically alter the harmony. Done correctly, performance tuning transforms adequate storage into a finely tuned resource that maximizes both cost efficiency and user satisfaction. Multi-region design is increasingly relevant as organizations expand globally. Placing data in multiple regions reduces latency for distributed users, provides resilience against regional outages, and helps meet data sovereignty requirements. Object storage often makes this easier, supporting replication or policy-driven placement across regions. File and block storage can also be distributed, but with more complexity and potential cost. The trade-off lies in balancing availability with performance and compliance. For example, a global video streaming platform benefits from distributing content close to users, while a financial institution may need to keep certain records within national borders. Multi-region strategies therefore require careful planning, weighing technical needs, legal requirements, and cost. Done well, they provide not just resilience but also a better experience for users worldwide. Done poorly, they can introduce complexity without delivering meaningful benefits. Cost governance in storage is about more than just controlling capacity. It involves monitoring how storage classes are used, tracking retrieval charges, and managing data transfer fees. Object storage, for instance, may charge less for storing data, but more for retrieving it from cold tiers. File storage costs can grow with heavy concurrency, while block storage bills accumulate through provisioned volumes even when underutilized. Cost governance tools help organizations track and forecast expenses, enabling smarter use of tiering, lifecycle rules, and access patterns. Without governance, cloud storage bills can balloon unexpectedly, consuming budgets and undermining trust in IT teams. Effective governance requires both technical insight and financial discipline, ensuring that data is not only safe and performant, but also economical. It reinforces the idea that in cloud computing, storage decisions are as much about economics as about technology. Security monitoring closes the loop by ensuring storage systems are not just functional but also trustworthy. Cloud providers typically produce audit logs that record who accessed what data, when, and under what conditions. These logs can reveal suspicious behaviors, such as repeated failed access attempts or unusual data transfers. Integrating audit logs into a security information and event management system allows for automated detection of anomalies, policy violations, or exfiltration attempts. File storage can be monitored for permission changes, block storage for unusual I/O patterns, and object storage for anomalous API calls. This constant vigilance turns storage from a passive container into an actively protected resource. Without monitoring, organizations may not realize a breach has occurred until it is too late. With it, they can respond swiftly, preserving trust and meeting compliance obligations. Data disposal is often overlooked, but it is as critical as data creation. Secure disposal ensures that sensitive data does not linger after it is no longer needed. Methods include crypto erase, which destroys encryption keys to render data unreadable, and secure delete processes that overwrite data multiple times. For physical media, certificates of destruction may be required to prove compliance. Improper disposal can lead to breaches, regulatory fines, or reputational harm. For example, discarded storage devices without proper erasure have led to sensitive information leaking into the public domain. Disposal must therefore be an intentional part of the data lifecycle, not an afterthought. By ensuring data is permanently removed or rendered inaccessible, organizations reduce risk and honor both legal and ethical obligations. Vendor portability is another concern as organizations seek to avoid lock-in. Cloud providers often offer export tools and formats for moving data between services, but these vary in completeness and ease of use. Rehydration time, the delay in retrieving large amounts of data from cold or archived storage, can also impact portability. Planning ahead with standardized formats, migration tools, and contracts that specify exit procedures reduces the risk of being trapped. Without such planning, organizations may find themselves tied to costly providers or struggling to comply with new regulations. Portability should be considered at the start of a project, not only when exiting becomes necessary. By embedding portability into storage strategy, organizations protect themselves against both technical and business shocks. Recognizing anti-patterns helps avoid common pitfalls in storage design. Concentrating all data in a single bucket creates a massive point of failure, while leaving storage publicly accessible exposes sensitive information to the internet. Untested restore procedures are another anti-pattern, offering false confidence until disaster strikes. These mistakes often arise from convenience or oversight, but they carry severe consequences. Avoiding anti-patterns requires discipline, governance, and regular testing. The goal is not perfection, but resilience, ensuring that systems can withstand mistakes, attacks, or unexpected events. By learning from these failures, organizations strengthen their approach, building storage environments that are both secure and sustainable. For learners, the relevance to certification exams lies in being able to match workload requirements with the right storage semantics and controls. Exams may test understanding of when to choose object over block, or how lifecycle rules enforce retention policies. More broadly, the knowledge translates to real-world scenarios where professionals must balance performance, durability, compliance, and cost. The ability to justify a storage choice, not just technically but in terms of business and regulatory needs, is a marker of professional maturity. By mastering these concepts, learners not only prepare for exams, but also for the responsibilities of designing and managing storage in dynamic, high-stakes environments. In summary, selecting the correct storage model involves far more than raw capacity. Object, block, and file storage each bring unique semantics, performance profiles, and security considerations. Layered controls such as replication, encryption, monitoring, and lifecycle policies ensure that data remains durable, available, and compliant over time. By carefully analyzing workload needs, from access patterns to regulatory obligations, organizations can map requirements to the storage model that best delivers resilience and efficiency. This disciplined approach prevents common pitfalls and ensures that data systems remain trustworthy foundations for cloud operations. Storage is not just about where data rests. It is about how well it serves the mission of the business that depends on it. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.